Session 3.5 Rational Functions, Graph, Applications, and Models. Rational function. A function f of the form f of x, px over qx, where px and qx are polynomials, and qx cannot be equal to 0, and this is the rational functions. Rational function. Some examples of rational functions are, so this is a polynomial, it can be only constant, over x. So 1 over x, that is a polynomial over a polynomial. So this is the rational functions. And this one, x plus 1, polynomial over quadratic equations. So this is the rational functions. Okay, and this is another examples. Since any values of x such that q of x equal to 0 are excluded from the domain of the rational functions, this type of function often has a discontinuous graph. That is, a graph that has one or more breaks in it. So look at this example, 1 over x. Remember we say that the denominator cannot be equal to 0. Okay, so at this example, x cannot be equal to 0. So you're gonna see this is a discontinuous graph. Same idea with these two examples. The denominator cannot be equal to 0. The reciprocal of function. The simplest rational function with a variable denominator is the reciprocal of functions. So now I want you guys try to plug in the points into the f of x. Find out what is the y here, and then try to sketch this graph. Once you're done, just try to fill in this information. Okay, so first one, when x equal to -2, I will have a 1 over -2. And -1, there will be 1 over -1, which is going to be -1. Okay, this one, when x equal to 0, y will be undefined. Okay, x cannot be equal to 0. So check your work. Okay, based on those coordinates, we're gonna sketch the graph. You're gonna see this. When x equal to 0 at this point, y will be undefined. Okay, if you try to plug in the points closer to the 0 here, this is a -0.5. You could try -0.4, -0.3, -0.2. You're gonna see the graph will be approaching to x equal to 0, but not touching it. Okay? And then same idea for like the positive one. So we're gonna say it is discontinuous at x equal to 0. Because at this point, we're gonna get undefined. And then f of x is decreased on the interval. Which part is gonna be decreasing function? Both of them, right? This is going down here, and this one is going down here. So the decreasing function, that will be from -infinity until 0. Make sure you use the parenthesis not equal to 0. And here, starting from parenthesis 0 to positive infinity. And then the domain, that will be the same thing, right? Range. For the range in here also, the graph here is going to be approaching to the x-axis, but never touching it. Same idea for this guy. Right? So y cannot be equal to 0 also. If y equal to 0, then x will be undefined. Okay? So the range will be from -infinity to 0, or from the 0 to positive infinity. And then vertical asymptote. Remember what is the asymptote? This is the equation that the graph is gonna be approaching to it, but not touching it. So how to call the y-axis here? This is called x equal to 0. And then we do have a horizontal asymptote. This is called x-axis. That will be y equal to 0. It is an arc function and its graph is symmetric with respect to the origin. So remember what is the arc function? Let's talk about it. What is the meaning of arc function? Arc function is talking about when you have f of negative x, you're gonna plug in the function with the negative x. That will be equal to negative of f of x. For this example, let's try. We do have the function that is equal to 1 over x. Now, let's try to plug in the negative. That will become like this guy. All right, and then I could get out the negative here. And 1 of x, that will become fx. So I do have a negative f of x. So I fulfill this requirement, f of negative x equal to negative f of x. When you have the arc function, then the graph is symmetric with respect to the origin. Okay, will be symmetric to the origin here. Okay, example 2, we have this function x. F of x is negative 1 over x minus 3. Okay, since we already graphed the f of x equal to 1 over x, you could consider this is the parent graph. And then we could use the transformation to graph this guy. Okay, so think about it. This is talking about we paste the x with x minus 3 into this function. Okay, f of x minus 3. So that means we're gonna shift the graph to the right hand side 3 unit. Okay, and then we have the negative here. And then we have a negative. So negative of the f of x, that will be reflected by the x-axis. Okay? So you should have the graph like this. Shift the whole graph to the right 3 units. So before we do have a x equal to 0 has an asymptote. When you shift 3 units to the right, that will become x equal to 3. Okay? And then the previous graph, let's look at it one more time. It's supposed to be looks like that. And since we have a negative, so that will be reflected by the x-axis. So this guy be going up here, this one going down here. And that's why we have this picture. Okay, now answer the question. It is discontinuous at, look at the denominator. When I said x minus 3 cannot be equal to 0, right? So x gonna be equal to 3. So we're gonna say x equal to 3, that will be discontinuous. And f of x is increasing on the interval. So this is going to be going up. This is going to be increasing, right? And this is also the increasing. So that will be from negative infinity to 3, close parenthesis, or parenthesis 3 go to positive infinity. The domain will be the same thing. And then the range, that will be starting from negative infinity until 0, or from 0 to positive infinity. Okay, vertical asymptote. That's talking about this equation here. X equal to 3. And then horizontal asymptote, that will be y equal to 0. Okay. Okay, example 3. Reciprocal function f of x equal to 1 over x squared. Now, I want you guys try plug in the positive negative 3 into here. Find out what's the y. Once you're done, try to sketch the graph. Okay, check your work. Your graph should be looks like this. Okay, when x equal to 0, y is going to be undefined. So the graph is going to be approaching to y-axis. Same about like here. And then when y equal to 0, x is going to be undefined. So it's also approaching to x-axis. Okay, answer the question. It is discontinuous at x cannot be equal to 0, right? On the denominator cannot be equal to 0. And we have the f of x increasing on the interval. So that will be from negative infinity to 0. And then this is going to be decreasing, going down. So from 0 to positive infinity. The domain, that will be combine these two guys together. And then the range, since it cannot be negative, so the range will be parenthesis 0 to positive infinity. Vertical asymptote, that will be this equation, which is x equal to 0. Horizontal, y equal to 0. And it is an even function, and its graph is symmetric with respect to the y-axis. Let's talk about it. What is the even function? Okay, even function, we will have a negative function of negative x, that will be function of x. For this example, I have a f of x equal to x squared. So let's try to plug in the negative x here, right? And that will be, since there's a square, negative is going to be goes away. So this is going to be equal to f of x. So it fulfills this requirement here, even function. Okay, and even function, its graph is symmetric with respect to y-axis. Okay, with respect to the y-axis. This is going to be y-axis. Just like you have the mirror here, it's going to be copied from the left and the right. Example 4, we have this example. We could use f of x equal to 1 over x squared as your parent graph. So this guy, you could let another gx, that's 1 over x minus 2 squared. So this is talking about you're gonna shift to the right 2 units. Right? And then we're gonna times 2 here. So this is talking about I have a 2 times 1 over x minus 2 squared. Right? And then when you have the a here, and the a is greater than 1, remember, think about like the paragraph. Think about the graph is going to be narrower, right? Narrower, okay? So it's going to be closer to the y-axis. And then at the end, you have this function x. X minus 2 squared, and then you're going to minus 4. So that means you're going to go down 4 units. Okay, so look at our example here. Okay, we're gonna shift the graph 2 units to the right, okay, because of x minus 2. And then sketch the graph vertically by a factor of 2. And then shift the graph 4 units down because subtract by 4 here. So you should have the graph like this. Okay, it is discontinuous at x equal to 2, right? X cannot be equal to 2. And then f of x is increasing. Here, gonna be increasing. So that's from negative infinity until 2. And then decreasing, that will be from 2 to positive infinity. The domain, that will be added this up together. Okay, range, starting from here. Parenthesis, negative 4 until positive infinity. Okay, vertical asymptote. Okay, this is gonna be your vertical asymptote, x equal to 2. Horizontal asymptote, y equal to negative 4. Okay? Asymptote of rational functions. Let f of x be the rational functions. So I do have 2 polynomials in here. How can we find vertical asymptote? Vertical asymptote. Find any vertical asymptotes by setting the denominator equal to 0 and solve for the x. Okay, we're gonna look at this part here. Set it equal to 0 and solve for your x. If a is the zero of the denominator, then the line x equal to a is a vertical asymptote. Okay, just like here. We're gonna set this guy equal to 0 and then solve for your x. So x equal to 2, that will be the vertical asymptote. Horizontal or slant asymptote. If n strictly less than m, what is n? N will be the highest degree on the numerator. Okay, and then you're gonna compare the highest degree of the denominator. So n and m here. If n strictly less than m, then f has a horizontal asymptote, y equal to 0. If they are equal to each other, okay, they do have the same degree from the numerator and the denominator, then we do have the horizontal asymptote, y equal to an over bm. C, if n greater than m, okay, so the numerator, the degree is higher than the denominator of the degree, then f has a no horizontal asymptote. D, if n equal to m plus 1, okay, when m plus 1 is equal to n, then there will be an slant asymptote. To find it, divide the numerator by the denominator and disregard the remainder. So we're going to divide it. Px divided by the denominator, the qx, and then we just ignore like the remainder. The graph of a rational function may have more than one vertical asymptote. Remember, vertical asymptote depends on your qx here. Okay, we're going to set this equal to 0 and then solve it. Or it may have none at all. Sometimes we may not have the vertical asymptote. The graph cannot intercept any vertical asymptote. There can be at most one other non-vertical asymptote. And the graph may intercept that asymptote, as we shall see in example 6. We're going to look at it. Find all asymptotes of the function. So we do have a rational functions. First, we're going to set the denominator equal to 0. And then we want to solve it. Factor out, you're going to get x plus 2 times x minus 3. So x equal to negative 2 and x equal to 3. So these two equations are the vertical asymptote. And then we're going to look at horizontal asymptote. The n is going to be equal to 1 here, right? The highest degree of the px. N equal to 1. And then m equal to 2. Okay, so we're going to look at this table. N equal to 1 and m equal to 2. Okay, so that will be in the case A here. F has horizontal asymptote, y equal to 0. Okay, y equal to 0, the horizontal asymptote. B, try to do it by yourself. Find the vertical asymptote first, and then look at the degree for the px and the qx to see if they do have any horizontal asymptote. So vertical asymptote, x plus 1 equal to 0. So x equal to negative 1, that will be the vertical asymptote. And then horizontal asymptote, n is equal to 1, m is also equal to 1. Okay, so n equal to m. There is a horizontal asymptote. We're going to use the coefficient of this guy. So 4 divided by the coefficient of the x, 4 over 1, which is going to be y equal to 4. Okay, y equal to 4, that will be horizontal asymptote. Okay, C, x minus 1 equal to 0. So x equal to 1, that will be vertical asymptote. And then the n is equal to 2. M is equal to 1. Okay, remember, we go back here. When n is equal to 2, m equal to 1. So if we fulfill the case D here, n equal to m plus 1, then there will be an slant asymptote. Okay, so what we're going to do, we're going to divide the numerator by the denominator. Okay, numerator, we do have 1, 1, and 0. Okay, numerator divided by the denominator, which is x is going to be equal to 1 here. Okay, use the symplectic division. We bring down the 1 here, multiply it, add it up, multiply it. So we're going to get the 2 here. Okay, we just ignore about the remainder. So the equation of the slant asymptote will be y equal to x plus 2. Okay, this is a degree of 2 here, so we subtract 1. So this is going to be 1x plus 2. So that would be the equation of the slant asymptote. Let fx equal to px over qx. Define a function where p of x and q of x are polynomials, and the rational expressions is written in lowest term. To sketch its graph, follow this step. First, find any vertical asymptote. We're going to set q of x equal to 0 and then solve for the x. And then find any horizontal or slant asymptote. We're going to compare the highest degree of px and then the highest degree of the qx. Find y-intercept by evaluating f of 0. So we're going to plug in x equal to 0, find out the y. That will be your y-intercept. And then find the x-intercept. This time we're going to set f of x equal to 0 and then solve for your x. Determine whether the graph will intercept its non-vertical asymptote y equal to b or y equal to mx plus b by solving f of x equal to b or f of x equal to mx plus b. Okay, remember the graph will not intercept the vertical asymptote, but it may have the chance that it intercepts the horizontal or the slant asymptote. So how can we find it out? So when we have a horizontal asymptote or slant asymptote, you could solve it by using the f of x, make the px over qx equal to b, solve for it, or f of x equal to mx plus b. Plot selected points as necessary. Choose an x value in each domain interval determined by the vertical asymptote and the x-intercept. And then complete the sketch. Graphing a rational function with the x-axis has horizontal asymptote. So first, we're going to find out the vertical asymptote. Set up this guy equal to 0, okay, the denominator. Factor out, you're going to get x equal to 1/2, x equal to -3. Okay, any horizontal asymptote, n equal to 1, and then m equal to 2. Okay, so y equal to 0 will be the horizontal asymptote. Now we're gonna find the y-intercept. We're gonna plug in x equal to 0, so you're gonna get -1/3. Okay, x-intercept. We're gonna put the fx equal to 0. Solve for it, so x is gonna be equal to -1. So we do have x-intercept and y-intercept. And then we're gonna double check to determine whether the graph intercept is horizontal asymptote. We're gonna solve f of x equal to 0. Okay, make this guy equal to 0. So we're gonna get back to the -1 and 0. Okay, -1 and 0. This is our x-intercept, and it also intercepts the horizontal asymptote. Okay, so now we're gonna combine everything together. First, we do have a vertical asymptote, x equal to 1/2. Okay, so let's put 1/2 about like here. I use the dot line to represent the vertical asymptote. And also, I do have a x equal to -3. So 1, 2, 3 here. And then for horizontal asymptote, we do have a y equal to 0. Okay, y equal to 0. That will be on here. Okay. And then we do have y-intercept. X equal to 0, y equal to negative 1/3. Okay, x equal to 0, y equal to negative 1/3. So somewhere like here. And then we have the x-intercept. X equal to negative 1, y equal to 0. Okay, so like here. Okay. And then I'm gonna break it down for the interval. So that will be from negative infinity until negative 3. This is gonna be the negative 3, the vertical asymptote. And then from negative 3 to negative 1. Okay, negative 1 because this is gonna be the x-intercept. Pass through the horizontal asymptote. And then from negative 1 to 1/2. Okay, 1/2 will be this one. Okay, and then from 1/2 to the positive infinity. Okay, we try to cut it down for the domain, and then we're gonna test for the point. So I just pick some points that's within this interval. So from negative infinity to negative 3, I'm gonna pick negative 4. So somewhere like here. And then, okay, negative 2 will be in between negative 3 and negative 1. So this is 0 and 2. Okay, then value of f of x. So we try to plug in the test point into the f of x here. Once you plug it in, you should get like this number. Okay, so we only care about the sign of f of x. Okay, so this is a negative, I'm gonna put the negative. Positive, I'm gonna put the positive. And then graph above or below the x-axis. So negative, from negative infinity to negative 3 here. This is, we got the negative. So we're gonna graph below the x-axis. Okay, below the x-axis. So you could see from here, I will be going like this, approaching to the asymptote and somewhere approaching to the vertical asymptote. Okay, and then second part from negative 3 to negative 1. So we print here positive. So I will pass through this point and then going up here. Okay, approaching to the vertical asymptote and then pass through this point. From negative 1 to 1/2, that will be negative. So pass through this point and then going down, okay, below the x-axis. And then from 2, it will be positive. So gotta be above the x-axis. So something like here, like this. Okay, I didn't do a good job at this part. Let me try it one more time. It should be really smooth to go here, and then approaching to vertical asymptote. Okay, so it should be looks like this. Okay, if you want, you could try to plug in some test point here. Okay, this one. Do the same thing. First, find the vertical asymptote. So that will be x equal to negative 1. Horizontal asymptote. N equal to 1, m equal to 1. So we have a y equal to 4. And then y-intercept, put x equal to 0, so you do have a negative 2 here. X-intercept, we're gonna let this guy equal to 0. So x equal to 1/2, right? Okay, since we do have a horizontal asymptote, we're gonna try let the f of x equal to 4, okay? Multiply x plus 1 for both sides. Okay, you're gonna get negative 2 equal to 4. This is the false statement. That means the graph does not intercept the horizontal asymptote. Okay, so we cut down like this free interval. So when we have these test points, we're gonna plug it in. Find out what did you guys get for the f of x. First one, that will be negative 12 minus 2, so negative 14 over 2, negative 2, so it should be 7. Right, plug in one by one. So this is gonna be positive, negative, positive. And when you have a positive, means you're gonna graph above the x-axis. When you have a negative, you're gonna graph below the x-axis. Okay, try to combine all the information together. Okay, horizontal, y equal to 4, asymptote, x equal to negative 1. Okay, and then plug in the x-intercept, y-intercept. That's it.